David Enfield. I've been working here as an oceanographer since 1987. I worked with, in the climate group, Song-Ki Lee and Junsai Wang and others. So what I want to talk today about is an interesting experience I had earlier this year when I got a phone call from a friend of mine in Peru. He's a very dear friend. We went to graduate school together at Oregon State University. And so one good day, Antonio calls me up and he says, Dave, we got a problem down here. What can you tell me about the effect of El Nino on the rainfall in the Amazon region? I said, well, I used to work on ENSO, but I haven't heard of any papers that talk much about the Amazon. And he was specifically concerned with this one small area just east of the Andes in Peruvian territory. I said, no, I don't think anybody knows anything about that. And he says, well, gosh, if you can't tell us, we certainly can't do it. And he says, we're worried to death about what this El Nino in 2014 can do to us, because we have these oil operations back there, the Spanish consortium for oil exploration in Peru, and they had a base camp and everything all set up. In 2011, the base camp got wiped out by flooding. And so they said, well, El Nino is known for flooding, so we're really worried. Anyway, I couldn't tell him over the phone, so he sent me an air ticket to go down to Lima and work with him to try and figure it out. And that's what this talk is about. So, gotta do that. Yeah, there we go. So I'm going to develop the talk in two parts. First, I want to talk about the impact of El Nino at the largest scale, namely all of northern South America, really tropical South America. Talk about data set selection, this large-scale analysis, break it down by regions, and I'll discuss some of the mechanisms that we think are at work there. And then I'll go into this study that we did in Lima of this Amazon watershed where they have their operations. I'll talk about characteristics of that region and the motivations for doing the work, and we'll look at just a brief analysis of the precipitation and river discharge and what we learned from that. So this is a course data set. It's a reanalysis of precipitation that NOAA has, called the TREC. It has a 2.5-degree horizontal resolution, and the region that I'm going to be talking about in the second part of the talk is this watershed here called the Ucayali River watershed. Now, at the largest scale, you can see that what predominates is negative correlation with ENSO, with an ENSO index 3.4, meaning that most of that area is dry during the winter of El Nino, but there are regions that have more rainfall than usual, but the significance may not be that great. We can't see a lot with this data set. It's just the resolution is too poor to resolve the interesting processes that must be going on. So, and this is the region where you can really see it. This is the Ucayali region. That red rectangle here, this is the region where the company has its oil lease, and they're doing their operations. They're called CEPSA Peru. And here are the only two grid points in that data set that we find within that area. So it really is totally inadequate to use that data set. Over here is the central massif of the Andes, and then some of what we would call mountains, but they could probably call foothills. And up at the top here is a city called Pucallpa, which is in the forested area of the Peruvian Amazon. This, of course, is Brazil. And so the whole area is sandwiched between the Andes and the Brazil border. So the problem then is, I'll show you some analysis we did with that low-resolution data set, but it was really unsatisfactory. So we decided to try and get more information by using the high-resolution data set. And there were two available at the time with the help of Song-Ki Lee and Jay Harris. I was able to get a hold of these. Sorry. I always forget to turn these things off.
David, I just want to point out
that
that ERA is ECMWF, not really nothing to do with the ECMWF insurance.
Where?
This, right, I know. There. That's not no
This one?
Yeah.
Yeah, I think you're right. It's not, yes, not knowing CCMWS, that's right. We used that data set for some of the other things. What we finally wound up using, though, was the trim data set. It's a shorter one, but I think it's a very good one. And for the purposes of looking at the climatology of the rainfall and its relationship to El Nino, it actually worked out pretty well. So I'm happy that we used the trim data set. I wanted to get familiar with it anyway, and it was suggested by somebody here in the lab. So in this large-scale analysis, I'll be looking at the correlation of the ENSO index, El Nino 3.4, with the precip. I'll talk a little bit about the seasonality of that relationship, and I'll look at the specific impact over some of the regions in Northern South America. Then I'll look at some possible mechanisms for what we see, things such as the Walker circulation, air mass modification, or CAPE, and topographic effects. So, all right, this is the October to December season from 1998 to 2014. We're showing only the correlations above the 95% significance level. And so you can see that there's this one large region here just north of Manaus. There's another region that looks very suspiciously like the ITCZ. And then we have this region over Colombia and Ecuador that is also dry. There's an area of wetness in the coastal region of Ecuador. And then we have a spotty distribution of negative correlation running down the Andean region towards Chile. There is a hint of something positive going on here, more rainfall. It's well known in this region we're having more rainfall during El Nino. And generally speaking, we do expect dry conditions in much of northern South America. So that's not particularly new. Now here's what the correlations look like if you show all correlations. And this is also not just for October to December, it's for all months. And if we then restrict it to 95%, you can see that all months is very similar to what it was before, just for October to December. We're primarily interested in October to December for reasons that I'll show you in the second part of the talk, because that was the period that they were especially interested in. And so here we are once again, and looking at these various regions. And now I want to take that away and show the topography of South America, because that's going to be important in what we're talking about. And so, of course, all of this is flat. It's what we call the Amazon generally. and except for these highlands in western Venezuela, it's all flat. And then, of course, we have the Andes over here, running from Colombia down through Ecuador, and, of course, down through Chile. So these are some of the regions that we can identify in the correlations. So we have the IPCC region, we have the lower Amazon, we have Colombia, we have Ecuador, we have Valley that I'll talk about in the second part of the talk. There's this region down here that I call the Three Corners region. It's where Paraguay, Brazil, and Argentina come together. I'm not going to be talking about that region. It's pretty well known that it gets rainy with El Nino. I'm not really going to talk about it. I'm not going to talk about Nordeste. I show it mainly because it's a well-known region for being dry during El Nino, and it's a region that's normally dry. All right, but it turns out that over the months that we were primarily interested in, it really doesn't have much of an effect. So there's not much reason to talk about it for that time of year. So this is what the correlation map looks like when it's superimposed on topography. So we have this large area in the lower Amazon, for the most part, very low elevation, and this large area of dryness during the winter of El Nino. And then over in Colombia, it looks like the high elevations are the ones that are affected by dryness, and then over here along the coast, close to the equator, we have a lot of rainfall. And with the Ucayali region, we can see that significant correlations are mainly in the northern part of that region. So let's look at the Ecuador region in more detail. So this is the zoom in on the correlation map for Ecuador. This is the topography. See there. This is what the positive correlation looks like. So all of this region tends to be quite rainy when you have in the October to December period of El Nino, also in January to March. And then this is what the negative correlations look like. What we can see is that in the mountainous region, it's the negative correlations that hold sway, whereas the coastal region pretty much peters out. The positive correlation peter out before you start going up to the higher elevations in the Andes. This is most likely due to the fact that with El Nino, you have a lot more moisture in the planetary boundary layer, but that moisture anomaly tends to be confined to the planetary boundary layer. So it's about the first kilometer, at most kilometer and a half, where you have a modified air mass that can give you rainfall. So it really doesn't go up into the high mountains. Here, once again, is a zoom in on the part of the map of the correlations for northern Ecuador and Colombia. This is the topography map, and this is the distribution of rainfall. And so you can see that mainly the rainfall anomaly, the dryness, is confined to the Andean region. What's probably related to certainly the lower Amazon dryness, it's almost certainly going to be related to the water circulation. This is the normal water circulation when we're not having an El Nino or La Nina event. And it's a well-known region of convection over in Indonesia, and descent or subsidence of the atmosphere in the eastern Pacific, and then another region of convection over the Amazon. So that's the normal situation. But during an El Nino event, of course, we know that there's a lot of positive SSP anomaly in the central and eastern Pacific that causes the Indonesian convection region to migrate eastward, and the tendency, the anomalous tendency for subsidence to then take place over South America. It doesn't mean that it's subsidence in the absolute sense. It's in the relative sense, of course. There's still convection going on, but there's less of it, and that's the situation. The way we try to measure or characterize the Walker circulation is by using what we call the 200 millibar velocity potential and irrotational wind. So the meteorologists in the audience obviously know about this. This is what, on the left, we have the normal situation, and this is the velocity potential with the contours and the irrotational velocity with the arrows. And down below we have the mid-tropospheric vertical velocity, 500 millibar vertical velocity. So this is at the top of the troposphere. This is at the middle of the troposphere. So we can see here the normal situation is over northern South America. We have a divergence in the upper troposphere, which is what you expect with a region of massive convection. When we go to El Nino, what we see, of course, is that the centers of convection have moved eastward in both cases, and now the anomalous velocity potential and the irrotational wind is a convergence over northern South America. In the vertical velocity, the absolute vertical velocity normally is upward, as we would expect, and the anomalous vertical velocity is downward. So if we go back to our map, our topographic map, with the rainfall correlations, and put our anomaly of velocity potential on top of it, we can see that it corresponds very nicely to that large area of negative correlation over the lower Amazon. So this seems to be the most reasonable explanation for the dryness in general over northern South America, is this very large anomaly of velocity potential, which basically says that you have an anomalous subsidence over that region, which tends to heat up the troposphere and dry it out. It modifies a skew-T diagram, a vertical profile of temperature and humidity in such a way that the atmosphere becomes more stable, more opposed to convection taking place. But then, of course, the question is, well, exactly what is happening over here? Obviously, it must have something to do with the high elevations. I think probably what's going on is that as you go away from this central region, the degree of air mass modification lessens. And so you see over this low area here, the rainfall anomaly is no longer significant. There's probably still a modified air mass, but it isn't until you get to the Andes where the remaining anomaly in the air mass really becomes evident, because you get orographic uplift of the air mass, and then the effect is you don't have the amount of CAPE in the atmosphere that you would like to have in order to get a normal amount of precipitation over the mountains. This is what the CAPE looks like. So we have modified air mass clearly over this entire region here. It's predisposed to dryness. It's more stable. And we also have that same thing over the Andes. So the summary of the large scale then, lower Amazon basin is dry during El Nino. Topographic effects appear unimportant there. The impact can be attributed to reduced convection due to modification of the water circulation by the altered SST distribution. The ENSO-related dryness in the Andean regions of Ecuador and Colombia appear to be related to the interaction of the Amazon air mass modified by the water circulation with the topography of the Andes. The coastal zones of Ecuador and northern Peru receive more rainfall during El Nino because of a more moisture-laden and unstable air mass over the warm Pacific SST anomaly. And the coastal rainfall anomaly does not affect the Andes, most likely because the air mass modification is confined to the planetary boundary layer. So this is the second part of what we actually did in Lima, looking at this small region on the east side of the Andes. This is the Ucayali River, the large Amazon tributary that flows northward. This is what it looks like. If you put it on a map, this is the area of the oil lease that they were concerned with. There's a small river, well, small maybe by their standards, certainly not by ours, but it's a tributary to the Ucayali. This is the Ucayali running up this valley right here. These are the headwaters of the Ucayali, and this is the lowland region. And that city I mentioned, Pucallpa, is up here. We can't see the central massif of the Andes. It's over here somewhere. And but here's an important mountainous area here, and another one right there. Here's another valley with another tributary, and so forth. Now here we zoom in on the region of that oil lease, and we can see more detail in the map of the river. Notice it has cut-off oxbows, as some people call them, where the river used to be. And in fact, if you think about it geologically, this is the reason there's petroleum there. Because this is what large rivers do. They meander. And as they successfully meander back and forth across this valley, they inundate the vegetation, and eventually it gets buried geologically, and it turns into petroleum. So no surprise. And so these rivers do what they do, and that's a problem for these petroleum geologists. What I'm going to show you here is an animation of what that river does over a 10-year period, and I'll repeat it a couple of times so that you can get a good idea of how that works. So there it is, and here it is, the animation over 10 years. In that red circle is the future drilling site that they selected some years ago, and they set up a base camp there, sent their people out there to do the explorations, determine the exact site of for the drilling, and so forth. So go back and run again. See how those meanders grow. They leave behind these sediment beaches like that on one side of the meanders. Here you can see ancient, well, maybe not so ancient beaches, and the meanders tend to move in this direction like that. So what happened over this period, now here we go, 2004, 2005, 2006. Notice how these two meanders started moving together, and eventually they connect, and then you get a straight section of river here, and this becomes a cut-off oxbow, or actually two oxbows. So we're actually seeing the same process that much earlier formed these other oxbows. Then, from 2007 to 2009, what we see is a huge acceleration of this particular meander here towards the base camp. Okay? So notice how much closer it is in 2007. And in 2008 and 2009, almost, it's getting close to that base camp. And this is what they were worried about, because by 2014, it was even closer. So, well, and the last thing I can say about it is that it's no accident that the acceleration occurs after those two meanders merge into a straight section, because now you have all the momentum of the river running right up there and then against these two meanders here, and so they spread apart.
Do you have data for 2014?
Not really from 2014. We were actually working on this in the spring of 2014, so we don't have data for the. We didn't have data for the latter part of the year.
The same kind of animation all the way through 2015?
Yeah, right. So this is a summary of the advance of the river over a period of time, 12-year period, and you can see how close it finally got in 2014 to that base camp. It was really very close. Now, why? That would be concerning. If you're them, you're worried, of course, about your base camp. But one reason why they're especially worried is because in 2011, they had this experience. Here was a period of time, it must have been around October of 2011. This was December of 2011, and look at how much, this is river flow, this is discharge. And the blue curve, that's the highs of all discharges over the history of the measurement. And the red curve is the lows of all the discharges. The green is the mean, and the magenta is 2011. And what was very worrying is that the river discharge increased tremendously at that particular time. All right, this is the base camp here, right? And this was the base camp in October, in this period here. Then you go to December, and we see all this flooding has taken place. Let's see where we go. I thought I had another picture here. The next one. So things changed a lot going from October to December, and created a lot of problems for us. Yeah, here we go, more pictures of the base camp in December, and obviously it created a lot of havoc for them. And in 2014, we're talking about March, April, when Antonio originally called me. You'll probably recall that NOAA and other agencies around the world were almost convinced this was going to be another El Nino like 1997, 1998, which was a disaster in Peru. And so they said, well, gee, everybody's saying this is going to be a big El Nino, and what we're accustomed to with big El Ninos is a lot of rainfall. Of course, rainfall in the coast, not in the Amazon. But they were very concerned. If they had this kind of a problem in 2011, what kind of a problem were they going to have in 2014? So this was the motivation for it. So this is the low-resolution precip data that I looked at the beginning. Up here we have the Nino 3.4 index for that period of time, October, December. These are the anomalies over roughly 35-year period. The large blue bars are La Nina events, the large red bars are El Nino events. And down below here we have the rainfall, monthly rainfall anomalies for those two grid points that I showed you in the Ucayali watershed. And here we have 2011. We can see that 2011 wasn't particularly anomalous in terms of the rainfall over that entire watershed, according to this data set. In terms of El Nino or ENSO, it was not an El Nino, it was actually a La Nina. So the large-scale analysis indicates that it should be a negative correlation. It should be dry during El Nino and wet during La Nina. In fact, they had a large river discharge, but there wasn't a lot of rainfall over most of that catchment. So the rainfall over the catchment doesn't really explain why they had such a large river discharge. They didn't have a really anomalous amount of rainfall over that camp. Okay? But they did have, the river came up 3 meters, and that's what caused all the problems. So this is the monthly river flow data taken at Pucallpa, the northern part of the catchment. And there was a discontinuity we found in the data right here. They must have changed some reference level. Obviously, the river doesn't undergo a change like that, so we corrected it. This is what it looks like after you do a correction to the two means. So now you have what looks like a fairly usable monthly anomaly data set for the river discharge that we can then go and compare to the monthly data for ENSO. And so when we did that, well, first of all, up here, these are the adjusted discharge data. And here is the monthly anomaly of the Nino 3.4. And down here are the seasonally averaged discharges for a different time of year in January, February, March. Well, between these two time series, what we get is a correlation of minus 0.18. The 95% significance level was 0.18. So this was barely significant in terms of the relationship between the discharge and the ENSO index. When we go to this particular way of looking at the analysis, it's about the same thing, slightly larger correlation than what the 95% level was for that, but still a marginal correlation. And in terms of variance explained, we're talking about only 2 to 3% variance explained. So historically, we cannot find a good correlation between ENSO and the river discharges either. So this is just the rectangle for the Ucayali region, and these are the grid points for the TRIM data. The correlation between TRIM and Nino 3.4 is indicated right here. This is the 95% limit of the negative correlation. And down here we have positive correlations of TRIM versus the discharge. Okay, so up here it's TRIM versus the El Nino index down here, we have trend versus the discharge, because we wanted to say, okay, well, clearly there isn't much relationship between discharge and rainfall over the entire region. So there must be a relationship somewhere in the region with discharge. So that's why we did this correlation down here and found these positive values. So here is our digital elevation model again. This is the Ucayali River Valley again. There's Ucalpa, where we measured the river discharge. Oh no. Oh no. What did I do? Let's get back.
I think you need to actually keep going up, please. Oh.
This is the beginning of the top. Somehow the
It looks like you have created next page.
the PowerPoint file got messed up here. Hang on. Find out. We go down here, right? Okay. Right here, we're almost through with the talk. How am I doing on time? I don't have a watch with me. No problem. Okay. Yeah.
All right. David, quit
Yeah.
that thing.
Yeah. Yeah. All right. Yeah. Okay. So go back and do that once more. Right. So here's the negative correlation rainfall versus ENSO. We can see that it's clearly in the lower reaches of the catchment, and the discharge versus rainfall is high at the high elevations. End of story. That's exactly what we would expect, probably, is that as the air mass gets lifted orographically, you're going to get more precipitation than you otherwise would. And so you might suspect, well, okay, so we have an air mass that doesn't want to correlate very well with anything down here, but it certainly does correlate with river discharge when the rainfall occurs over the mountains. Right? So what you might suspect then is that there's a relationship with wind. If the wind is northerly, the air mass, the moist air mass from the Amazon is funneled down into the upper reaches of the catchment and then precipitates as the orographic effects kick in. So you would expect the relationship between wind direction at the northern end and the precip in the headwaters region of the catchment, and that's basically what we see from year to year. At that time of year, around the end of the calendar year, beginning of the next calendar year, we tend to have northerly winds from north to south. And that's when they get their large river stages, when the river comes up. What happened in 2011 was there was a lot of rainfall in that headwaters region. What I don't understand is that there wasn't a lot of northerly wind that accompanied that rainfall. So my hypothesis about the wind isn't perfect by any means. I think it's probably a good general description of what happens, but it's not necessarily going to be the factor in every instance. So there's a lot more to be said about this region. I'll summarize the Ucayali work here. The El Nino historically has had little impact on rainfall in that region. The correlation with ENSO is negative, meaning that during El Nino conditions are dry, but it's very significant. It's only over the northern part of that catchment at the lower elevations, and doesn't really explain river discharges very well. Discharge relates mostly to rainfall in the upland headwaters part of the watershed, where the ENSO rainfall correlation is insignificant. The TRIM data set, I concluded, is a short data set, but it was very useful in this analysis, and I think I can recommend the TRIM data set for these kinds of studies. It gave me statistically robust results for that time scale. Appears to be not too sensitive to seasonality. It's especially well adapted for fine scale analysis in these tropical regions. TRIM is known to be a nice data set for the tropics. And wind data and atmospheric profile data from reanalyses should provide good diagnostics to try and explain better what happens both at the large scale and at the small scale. At the large scale, what we would really like to have is profile information so that we can actually detect the anomalies in the profiles of temperature and humidity with elevation, and be able to relate that to what's happening, especially over the mountains. So we can only surmise right now that it's a modified air mass that hits the mountains, and then it doesn't have enough instability in it to rain as much as is normal for that region. But to really nail that down, you have to have profile information. The data set that I would like to try would be GPS radio occultation. We had an interesting talk here some time ago by somebody who talked about GPS radio occultation. It's a very interesting technique, and I don't think it's ready for prime time yet, but I think in the future it would be a really good thing to try to apply to this problem, try and really understand how it works. So that's all I have for you. Hope it was interesting. Thank you very much. Chutai.
Very good talk, I like it. But I have a suggestion on comment for the first part of the talk. The suggestion is that answers, we have two types of answers, the so-called conventional and model P. And after 2000, almost all answers when is model P.
Model P.
And we know this. So your first part of calculation, use data starting from 1998. So if we use a model P index instead of medium 3.4 index, then I think the result of correlation will be much better. This is my guess.
Right.
Because after 2000, there's no conventional error.
Right.
Most answer is the model P.
Yeah, I agree. And we think that there must be a lot of difference in the telecommunications that occur, the climatic telecommunications that occur between those two types of ENSO. What could be done is to go back to that ECMWF data set, which is about twice as long as this TRIM data set, and would cover the period when we have these non-Modoki style ENSOs, and see if anything's changed when we look at that earlier part of the record. So it's a good suggestion. Thank you. I think there was something in the back. Yeah, hi.
I'd like to talk wondering if anecdotally what was 2014 like for the site?
Yeah, I haven't talked to Antonio recently. I think he would have called me if they had had a serious problem. So I suspect that probably they were okay. But still, just because of what the meanders were doing in the years previous to 2011, that particular meander is obviously very close to their operation. When the river flooded in 2011, it caused them almost $2 million worth of damage. And of course now the question in my mind is the economic factor of the price of oil. So when you take those two things together, the fact that the camp is endangered and the price of oil may not justify actually going through with the drilling project, I don't know what's going to happen down there. He may not know either, but it's something I'd like to contact him about and ask what happened. But anyway, I'm glad you convinced me to go down there. When Gavin said, okay, Antonio, just tell me one thing. Am I going to get to eat some good Peruvian food? So he said, don't worry. We'll be taking you out to the best restaurants in Lima. So I said, okay, you got a deal. So now I got to see about maybe working up a second trip to look at the aftermath. We'll see. So, yeah.
That's really very hard for that research profile. There's a sunlight, say the air, I think the standard has temperature in the water resources.
Infrared sounders?
Yes, I think
This is satellite system.
yeah, it's satellite. It started from 2002 on the at least for the ocean and the surface.
I talked to you about that. I have more. Yeah, that's going to be good. Yeah.
I'm just wondering, was snow melt ever considered for local system?
Yeah, that's a good question. No, we didn't think about snow melt. So October, November, December is the austral spring. So that's when you would expect snow melt. And it certainly is possible that that might have explained why we got that rainfall event at September 11th, when the winds weren't particularly strong from the north. So that's a good idea. That's something. So what we could do, Raul, the engineer who helped me with this analysis, Raul might be able to get me that information. He has a lot of information that he does anybody on the line have a question about the presentation? Nobody out there. Okay. Well, thank you very much for You think so, without the atmospheric profile?
No, yeah, profiles and motion.
If we could get the atmospheric profile, and then maybe what Chusai mentioned, because that is a question about the Modoki.
I'll say when you write a paper, I'll say you hold it. You got to.
This one, the red one.